Good morning to everyone. In today's video, we are going to see the short circuit and open circuit lines. So, in the name itself, it suggests that the line is short circuited and open circuit. So, now we will see in detail what will be the input impedance characteristics for a short circuit line and open circuit line. So, here we are considering a transmission line whose end whose load end is short circuited. So short circuited is nothing but you have terminated the line with impedance equals to 0. So ZR equals to 0. So when it is short circuited, almost the voltage will be 0. So if the transmission line is terminated with a short circuit, then the line is called as short circuited line. So for this line, I am interested to find out what will be the input impedance. So here the input impedance of the transmission line already we find out for a lossy transmission line. So in our last class, if you go through that video, you can able to find out the input impedance for a lossy transmission line. This is the equation. So I'm just simply take out that equation. In that equation, I just replace your value. Okay, I'm just replace the value whatever the ZL or ZR equals to 0 so I have to replace that one. So when I replace ZL equals to 0 whatever the input impedance of a short circuit line ZSC equals to Z0 into J Z0 tan beta L divided by Z0. So this Z0 will be cancelled over, so the final value is J Z0 tan beta L. So if you are considering general transmission line, that means in our previous video we just replaced for a lossy transmission line here alpha equals to 0. Without replacing this alpha equals to 0, if you find out the what is the solution, okay, what is the solution for the given general transmission line, you can able to get. So from that general equation, the short circuit transmission line ZSC equals to Z0 tan H hyperbolic tan gamma L. The reflection coefficient value of short circuit transmission line is k equals to minus 1. You may ask the question, how you can say that the k equals to minus 1. So already we know the coefficient of reflection. The coefficient of reflection is ZR minus Z0. K equals to ZR minus Z0 divided by ZR plus Z0. From here the short circuit line ZR equals to 0. So by replacing ZR equals to 0, the K value will be equals to minus Z0 divided by Z0. So which is nothing but equals to minus 1. Similarly for a voltage standing wave ratio, which is nothing but S equals to 1 minus modulus of K 1 plus, okay. So here K equals to minus 1, that is 1 plus 1 divided by 1 minus 0, okay, 1 minus 1, okay, 1 minus 1 equals to 0, which is nothing but your infinity, okay. So if I want to draw in variations graph, okay, variations of input impedance of a short circuit transmission line, I need to replace on x-axis beta L and y-axis ZSC. So ZSC I can able to find out from my given equation. ZSC equals to Z0. Either I can go for the general transmission line or I can go with the lossless transmission line Z0 tan beta L, okay. So on x-axis I replace with beta L. So here I can know the length of the transmission line as in terms of wavelength lambda by 2 or lambda by 4. When I go for the beta L, beta is termed as 2 pi by lambda. So for example, if I go with a quarter wavelength transmission line, L equals to lambda by 4, for beta L it equals to pi by 2. Likewise I can. So here if I replace with for transmission line 0 to pi by 2, the transmission line will be acts as an inductor, and for pi by 2 to pi it will act as a capacitor. Similarly, if I can go for the open circuit transmission line the same thing will be repeats. The load end is replaced with impedance equals to infinity. So the same place, here I am substituting ZL equals to infinity here. So while substituting ZL equals to infinity, not only here, for anywhere in your equations, don't directly substitute ZL equals to infinity. So take it common, ZL, take it common from here. So if I take it common, ZL and ZL here, it both will be cancelled over to each other. So it will be 1 plus j z naught by ZL into tan beta L. Likewise here also z naught divided by ZL plus j tan beta L. So then replace ZL equals to infinity. The leftover term, and this will be cancelled over, the leftover term ZOC equals to z naught into 1 divided by j tan beta L. So when I replace this denominator term into numerator, minus z naught j cot beta L. The same thing for your general transmission line, it will be z naught c z naught into cot h gamma L. Similar fashion for your reflection coefficient, ZR minus Z naught divided by ZR plus Z naught. So here if this value will become equals to infinity, so I just take it out common ZR term, so it will be 1 minus Z naught divided by 1 plus Z naught by ZR. So the leftover value will be 1. And similarly for your voltage standing wave ratio, it will be equals to infinity. So when you go for the variations in input impedances, here this is the way how you are getting, because there will be 180 degrees variation phase shift. Okay, so when I go for this, if the line is terminated, okay, if the line is terminated with a characteristic impedance, then that line is called matched line. So that means your ZL equals to Z naught. There the reflection coefficient equals to 0 and your standing wave ratio equals to 1. Thank you.